in how load forecasting fits with transmission planning. We've been able at Argonne National Lab to be involved in some technical assistance projects specifically related to Order 1920. And so we've enjoyed the chance to interact with states on those topics. And this kind of flows out of some of those conversations. And we've been supported by the Department of Energy Grid Deployment Office to develop these slides from some of that work and related work that we've done to give an overview and provide some education around these trends and how load forecasting fits into various transmission planning processes. So I'm David Sehloff. I'm an engineer at Argonne National Lab, and my background is electrical engineering. Much of my work is involved in modeling and simulation around transmission networks and how that interacts with planning. And my colleague Neal Mann also is here on the line and maybe able to answer some questions that come up and contribute to discussion. Neal, if you're able, would you like to give a quick introduction?
Sure. Thanks, David. Thank you. And also energy systems engineer. Here's really tried to think and make this
Neal, you're
not too deeply technical, but we can absolutely have questions that
Thanks, Neal. I think the connection might be a little bit of an issue, so hopefully we can have a chance to interact with if there are questions for Neal, but otherwise I'll do my best to answer anything that's in Neal's wheelhouse. So great. With that, I'll get started and walk through the slides that we have. So as we've mentioned, this is a brief overview of how load forecasting fits into transmission planning processes. And then we'll get into some of the basic details that are relevant to how we model data center electricity consumption. We're not assuming a technical background in any aspects of power system planning here. And we have 30 minutes with 10 minutes of Q&A. So what we'll go through here today is first of all, the role of load forecasting in transmission planning, starting with some context and then what are some trends and needs in load forecasting. And then really what we've been asked to talk about is the data center specific piece. So that's what we'll focus on, starting with a macro perspective and then zooming into what elements we can model within data centers and where that demand comes from. And we'll conclude with some of the big ideas and then questions that states can ask around these topics. And hopefully that's a good springboard for some more discussion. So starting with the role of load forecasting, I'll start with just to orient us an overview of some of the main transmission planning processes that we'll see. So starting with the major FERC order related to transmission planning, Order 1000. This order identifies planning regions that you see here on the map. And each transmission owner within a region has to participate in this regional planning process, as well as interregional coordination. And that process is led by the ISO, RTO, or the regional planning group within that region. Now, apart from that, transmission owners also conduct local planning. That's apart from this Order 1000 regional planning. And this regional and local planning can take a variety of timescales as well. So regional and local planning can certainly have a short-term planning cycle that's looking at near-term needs 1 to 5 years out. Order 1000 is really focused on this midterm of the 5 to 15 years. And that also applies to midterm local planning efforts. And long-term planning is also an important track. And Order 1920 sets some requirements around that, and then local planning certainly would also focus on that longer term aspect. Under 1920, this is defined at a 20-year planning horizon. So when we talk about transmission planning and how load forecasting fits into it, we need to keep in mind that there are significant distinctions of both the location and the temporal aspects of these planning processes. And so the application of load forecasting takes some different requirements depending on where and what time scale we're looking at. So those distinctions are important to keep in mind. But now that we've drawn those distinctions, let me generalize a bit and talk in a bit more general terms about what the transmission planning process is for and what it looks like. So really when we're doing transmission planning, we bring the best available information about the future state of the system and bring that into a detailed technical analysis that identifies a set of upgrades that are needed to meet reliability, economics, and public policy needs. And we want to do that with least regrets. That there will always be some degree of regret when we plan far into the future with big infrastructure projects, but we want to minimize those regrets to the extent possible. And this process takes three major steps. First is developing scenarios, constructing futures that are representative of what is likely to happen. Then translating those broad representative futures into the specific models that we need. And those are used in the needs identification, where we perform detailed reliability analyses using power flow simulations, we perform economic analyses using production cost simulations, and then from there we determine the specific needs for transmission. And after that, we can identify and evaluate potential solutions that would come out and solve those needs. And I want to emphasize here that load forecasts, maybe I don't need to say that to this group because there's certainly a recognition of this, but load forecasts are unique in having a significant influence on the outcome of the transmission planning process. And I want to illustrate that with an example. We have this power system. We might start with a forecast, very simplistic here, but we say that there's a very large data center that we're assuming will come online at this particular location in the network. So then that's the beginning of this scenario that we're developing. And then we'll do a capacity expansion to understand what generation needs to be added to meet this demand. So this determines that there may be new generation at this location in the network. From there, we do a reliability analysis and identify transmission needs, and we see all of these transmission needs that come from this future scenario with this large demand and the associated capacity expansion. But then the question comes up, what if the actual demand growth is different from that forecasted demand in location, in size, and in how much it relies on the grid versus on-site generation? That means that our capacity expansion generation additions will also differ. And then the transmission needs will differ. And that means that what we found in this analysis might overestimate certain transmission needs, and it might also underestimate transmission needs. So we really want to avoid that over and underestimating of what transmission needs are available. We don't want to build infrastructure that doesn't get used, that isn't needed, and pass that cost on to ratepayers. And we also don't want to underbuild and be left in a situation where we can't get new demand or capacity onto the grid when it might be needed. So a way that this is addressed in practice is to use scenarios in our planning. So here you see we consider that first scenario as scenario one, but then we consider alternative futures that might happen. In scenario two, maybe there's more distributed demand growth, and that might have a different outcome in the capacity expansion. Another scenario, scenario 3, that there might be co-located generation with that data center, and there might be some other types of generation that would be considered in the capacity expansion model. Using those multiple representative scenarios that do represent a range of possible futures, it allows the planners to identify how these needs differ and maybe persist across plausible futures. We can see there are a few transmission needs that persist across all 3 scenarios. There's one in particular. And then there are some that are unique to each scenario. So this gives an additional perspective to allow planners to see which transmission needs are really driven by different assumptions in these scenarios. And ultimately that mitigates the risk of over and under building when we take that additional perspective into account. So changing the load forecast assumptions, that's one component of the scenario-based planning that we really want to work towards. There are also a lot of other important components that we'll talk about on the next slide. And I'm going to make a distinction here between scenarios and sensitivities, which is another good approach to use in planning. Scenarios I think about as really a bottom-up, using different assumptions to identify different futures that are representative. Whereas sensitivities are more of something that's applied in the modeling phase where we vary certain parameters within those scenarios, but it's not necessarily a full change in our assumptions. Both of these are important to use and are used in best practices. An example of using sensitivities would be a 50-50 versus 90-10 weather scenario in a forecast where 50-50 is the future load has a 50% chance of exceeding the forecasted value, whereas the 90-10 means that it would have a 10% chance of exceeding that value, considering the axis of the weather conditions that drive uncertainty in that load growth. So applying both of those to capture that uncertainty in the load forecast that's inherent in that forecast is an important tool that's used in practice. Other examples would be using peak versus light load conditions in a power flow analysis, where we're looking at specific times to analyze detailed reliability outcomes. There are many sensitivities that can be and are used. So getting back to what goes into constructing a scenario, demand is one major piece, as we've touched on, but there are also a lot of other pieces that can be used to construct a good representative scenario. And I classify these broadly into estimates and best available information, and also uncertain variables. So a best available information might be a known utility plan. It's important to capture anything that is concrete in that way. Public policy is often something that we like to vary within our scenarios. The best information we have on additions of generation and retirement of generation, those are also important. Jump down to climate and weather, those are another set of important assumptions. And these different assumptions can go into both scenarios and sensitivities. But the better we do at creating these representative future scenarios, the better we can mitigate risk in our outcomes. So just in practice, what are the requirements and practice around these scenarios and sensitivities? It's very common to use one demand scenario, and this plot just shows the number of demand scenarios that are used in planning practice versus the number of demand sensitivities. It's very common to use one demand scenario and weather sensitivities, this 50-50 and 90-10, as I mentioned. A lot of planning processes will use other sensitivities as well. But there are other planning entities that do use 3 demand scenarios within their planning scenarios, and that includes weather and other sensitivities. So FERC Order 1000 doesn't have any specific requirements on how scenarios are used. FERC 1920 does have a little bit more specificity. It requires 3 planning scenarios, plus these sensitivities for weather or extreme conditions. But it doesn't specify how many demand scenarios we use. So it's fully compliant with Order 1920 to use a single demand scenario, but use that in constructing 3 different planning scenarios where maybe policy would be varied, but the demand would stay the same. So that's something to keep in mind, that there are differences in how many demand scenarios might be used. And then the last thing I'll mention here is FERC Order 896 that has led to the creation of NERC Transmission Planning 8 standard, which requires a consideration of a creation of extreme heat and cold benchmark cases, and then those are required to be used in planning, so that can intersect with both Order 1000 and 1920 processes, and other transmission planning processes. So that's just an overview of what's typically done in practice currently. And then we'll talk about some of the trends and needs in load forecasting. And I want to mention a report that gives a very good overview of this, that I think you all may find a good reference, from Brattle, Electricity Demand Growth and Forecasting in a Time of Change. It's from last year. And it touches on demand drivers and divides them into 3 broad categories. First is demand side resources, and these can have a major effect on demand trends, especially when they're aggregated. Nearly all utilities and RTOs in their forecasts do include demand side resources to some extent. There is work to be done in the detail and modeling of these, but it is something that is very typically included. Another category is electrification of both transportation and buildings. And these are also small contributions individually, but there are many of them. So when aggregated, this gives a continuous pattern of load growth. And these are included in many utility and RTO forecasts, not all, but many. It's best practice to include these, of course, and so an increasing number of forecasts are considering these. Finally, the focus of this talk: data centers, cryptocurrency mining, and then a related category of onshoring and industrial electrification. These are fairly different from the others, because each one is a large and discrete load, and there's high uncertainty about whether any given piece of demand, any given data center or cryptocurrency mining operation, or industrial electrification site would come online and connect to the grid. In this report, they surveyed the utilities and RTOs that included these in their forecast. In 2024, there were relatively few, but as of now, the numbers are quickly increasing. So that there are many approaches, and they are being considered much more. So we'll get into some more specifics about this in the coming slides. And then I just want to mention that as we're talking about trends here, besides these drivers, there is a need for more precise and accurate incorporation of climate and weather impacts to our demand. And so that's a significant need for forecasting going forward. That's something we won't touch on today, but that's a good topic for another day. So getting into forecasting data center demand, we'll start with a macro perspective here, looking at some broad trends and estimates. And first, I want to mention that there are some excellent sources that you can refer to on this. And one was actually given to a NARUC and NASIO group this summer in June of 2025. Greg Mandelman of Electric Power Engineers, supported by Lawrence Berkeley Lab, gave this talk on load forecasting for large loads. So I think you all may find this very relevant and interesting. It has great references and has questions that states can ask and actions that states can take. So if you haven't seen that already, I would recommend that. The slides and the recording are available on the NARUC website. One of the reports that's referenced there is from Lawrence Berkeley National Lab, looking at the energy usage of data centers as of 2024. And it gives an overview of methods and forecasts and probes into some of the forecasts and also considers an approach for what we'll see is known as bottom-up forecasting of data center demand. There's another report I want to mention that isn't referenced in those slides. It's from the Electric Power Research Institute, EPRI. It covers more of the trends and opportunities that can be taken to enable data center growth from both a system perspective and a data center innovation perspective. And it also includes some state-specific scenarios that might be of interest. So this Berkeley Lab report from 2024 gives a useful classification of different approaches to forecasting in three different bins. The first is bottom up. And this is a detailed model that looks at all of the power consuming components in a data center. And in many cases, it's specific to a particular data center installation. So this detailed type of modeling can be very accurate, but a challenge is that it's very complex to build these models. This Berkeley Lab report does release an open source model that can be used for bottom-up forecasting, so that's a great step forward in that area. But it still requires a lot of data. There's detailed information about what types of equipment is installed in this data center. And because of those specific data requirements, these true bottom-up forecasts are typically only something that we can apply for data centers that are known to be under the planning or construction phase. And that limits us to forecasts of just a few years into the future. Now, another approach is the opposite, top-down, where we take a very high-level model that uses just aggregated measurements at a country level or a regional level, and looks at the relationship between energy consumption and data volume through these data centers, and models that relationship, and then making assumptions on future data demands. It can get a sense of the future energy consumption that would be required. So it's a simple model. It has much fewer data requirements, but there are some limitations that it can't capture the specific characteristics of data centers, and we'll see later that there are many distinctions to draw. It doesn't consider efficiency trends, and it requires estimates of what the demand for data processing might be for the particular region of interest going into the future. Finally, the simplest approach is extrapolation. This just takes a baseline year power demand and assumes a growth rate and applies that growth rate to that year. So it's very simple, just using those two parameters. But we need to be careful about this approach because it's very sensitive to input assumptions. If the growth rate assumption is based on faulty assumptions, then the resulting estimated demand can be very unrealistic. And because of that, it's important to validate anything that's based on extrapolation. Now, in practice, it's rare to see a forecast that is exclusively one of these types of approaches. Most top-down models, for example, will have some sort of bottom-up approach to model the specific characteristics of the data center mix that they're looking at. It's difficult to get all of the data needed for a purely bottom-up forecast. So there may be some incorporation of top-down and extrapolation in those. And even if it's an extrapolation-based forecast, the assumptions need to come from somewhere. So they may be based on a bottom-up or a top-down model. So this can be a useful classification to understand what forecasts are looking like at their core in the methodology. So now I want to take a look at some of the major forecasts that we might see, these macro high-level forecasts that look at total global or in this case US-wide electric power demands from data centers. And there's a series of forecasts that have been developed looking at this growth between 2024 and 2030. And so we can see in the plot at the right, this figure modified from the Berkeley Lab report. There's a range in the estimated actual energy use, but we're getting to about 150 to 175 in 2024, and then the forecasts really diverge in some assuming a very large consumption, which according to this EPRI report I mentioned would be about 9.1% of the estimated 2030 US electricity consumption, down to a low end of 4.6%, which even that number is higher than the estimated current share of electric power use in the US. So here's just a table that shows some of these growth rates, and this compilation of these is taken from a report that was prepared by Evolved Energy Research for the SPP region. So there's a wide range. The question is, how should we consider these forecasts? So it helps to give a little bit of context to these. And first of all, we can't dismiss these forecasts because anything that's forecasted here would have significant impacts on power system needs. Any way we look at these forecasts, there's significant growth. But there are some caveats that we need to be careful about. The first is thinking about location. So these are US-wide forecasts, and there are location-specific forecasts. But we just need to be careful looking at these large US-wide forecasts. There's very high locational variation that we know we've already observed in data center growth. And so we can't easily look at a US-wide or even a regional forecast and assume that it translates easily to a specific state or service area. We need to make some careful considerations in how we look at those macro forecasts. Another caveat here is transparency. None of these methodologies are publicly available. They're proprietary forecasts, and so it's not clear from the forecast what what is assumed and how they use bottom up, top down, and extrapolation, and also making judgments of assumptions here. That's very difficult to parse out of these forecasts. So we need to consider that. And then finally, we should also consider some contrasting evaluations that that have come up in response to some of these forecasts. So one in particular from July of this year, from London Economics, a report titled "Uncertainty and Upward Bias Are Inherent in Data Center Electricity Demand Projections." It gives some cautions that that we may need to consider. The first is that there's an incentive to duplicate interconnection requests, and they point to some evidence that there has been a duplication of these interconnection requests. So using these requests as our ground truth for forecasts may be overestimating some of these, and particularly that there's a low financial barrier for a data center developer to put in this interconnection request, so that there may be incentive to duplicate those and leading to an overestimate. Another point that they raise is that vertically integrated utilities don't necessarily have incentives to have conservative forecasts. That may be up for debate, but the point that they are raising is that that they may not be so skeptical of projected data center growth being biased towards a higher growth. And then there are some other factors, including power system bottlenecks, local opposition, the degree of using on-site generation, and then the increasing costs of state incentives as this growth continues, that might not be considered in some of these high-level forecasts, these macro forecasts. And then finally, they do some analysis that says that looking at even the low end of these forecasted demands, there's a significant increase in the share of global chip supply that the U.S. would need to take to build these data centers between 2024 and 2030, where U.S. demand is less than 50% of the global supply. It would have to rise to 90% across the next 6 years. So these are some aspects to consider that are making the argument that there may be a bias upward in some of these forecasts. So how do we evaluate those ourselves? Well, I think to start with, it's very helpful to get an idea of some of the specifics and basic modeling approaches to looking at where data centers are using their electric power. So I'm taking a lot of these categories from a recent Argonne report that talks through data center power demands and on-site generation. There are variations across the types of data centers. So looking at whether a data center is an enterprise or internal, if it's a co-location data center where space is leased, this is a large area of growth. Cloud service providers, hyperscale, that's another major area of growth. These are large 100 or 200 megawatt data centers that the major firms are operating, and AI applications are certainly important there. Edge data centers are smaller and more distributed. High performance computing is more specialized for scientific applications. Crypto mining is also a major driver that uses specialized hardware, and it has very high energy demand, but the water use characteristics are a little different. Quantum computing is a big unknown. It's in the research stage now, but uncertain how that will play out in the future. there are different reliability tiers that apply for each of these. In the interest of time, I'll skip through some of this, but the Uptime Institute tier standard for topology is a great reference. It's not too long, but it talks through the tier 1, 2, 3, and 4 classification for how redundant and reliable the electrical supply system is. And just a note here, is that the tier standard is really based on the on-site infrastructure and doesn't consider utility supply to be a reliable source. So for meeting these tier reliability standards, it's really driven by the on-site generation and distribution topology. So a few operational metrics to keep in mind: power density, how much demand is needed per rack. We need better cooling if there's higher power density. The power usage efficiency, that's a very common metric. So that a lower number is better for efficiency. 1.0 is the most efficient that we can get. The water usage effectiveness is how much water is consumed compared to the energy consumed by the IT equipment. So looking at how that varies, how those characteristics vary across types of data centers, as we go down this table, we see that the contribution of these to energy consumption increases. At the bottom, we have some high and extremely high demand increases, and these are also very large facilities. Many of them are also at a high reliability tier. So tier 4 is the highest reliability requirement. And tier 3 is quite high as well. And you can see that the efficiencies also improve as we get down to these higher consumption and larger data centers. So here's just an overview. You can find this in this report. Might be a helpful reference. Looking at what the topology might look like for different reliability tiers. I won't dwell on this. This is also in the report and in the uptime tier guide. But if we're looking at a highly reliable tier 4 type of data center, we are looking at 2 independent distribution paths that are active at all times. And that often includes redundant generation in each path. So that there is a high degree of generation on site for these highly reliable data centers. And so whether the generation comes from the utility or from the on-site generation is really an economic decision from the data center perspective. And so just a little bit more detail. For tier 3, there's a requirement of N+1 on-site generation. So that means for N, we have the full demands of the site met with on-site generation for the servers and the cooling equipment. And then there's one additional generation unit that we need so that we don't have a disruption if we lose one unit. Under this, there's also a requirement for 12 hours of on-site fuel storage. Tier 4 is stricter. The requirement is that after any failure, there is N, so that the full power demands of the facility can be met. So that's at least N+1, but often you'll see N in each path. So that would be 2N or 2N+1, where you have N+1 in each path. And again, 12 hours of on-site fuel storage. Now this fuel is often natural gas, but it may be diesel as well. But there are a lot of options for this on-site generation. So I'm going to just conclude by briefly talking about some of our work at Argonne about nuclear-powered data centers. It's a promising source for both off and on-site data center demand. So this report that I've referenced a few times outlines how we might couple nuclear power plants with data centers. It looks at sizing and siting throughout the U.S. and finishes with a socioeconomic impact assessment. And just an overview of what we see here as some options for coupling a nuclear power plant on the left-hand side with a data center on the right-hand side. We outlined 5 options, whether the plant is co-located with the nuclear with the data center. Is there a separate grid connection, or is there is the connection exclusively to the nuclear power plant? And then does the nuclear power plant have a separate grid connection? So this is a very high-level overview. There are more details in the report, but we just wanted to highlight this as one option that is emerging as a way that that data centers could be powered locally with or without a grid connection. Here are some more details about that. It's categorized by how the connection would look, what this might mean for site availability, regulatory issues, both for nuclear power plant safety and power markets. So these are some interesting considerations in how this would interact with the power market, what the on-site generation capacity looks like, timeline, expenses, and those types of considerations. And then finally, the certainty of power cost for the data center owners is an aspect that's important to consider here. So that was just a quick overview of some of the work that we've done in the on-site power category. But whatever the on-site power looks like, it's an important consideration in forecasts. And so finally, to conclude, and maybe I'll just touch on the big ideas here and then open it up for questions and discussion. We saw that the uncertainty is high, and so to cover that, scenarios and sensitivities are very important to include in the planning process. So states can ask a lot of questions related to how transmission plans incorporate scenarios and sensitivities. The forecasts are also sensitive to assumptions, and there's a need for transparency in how forecasts are created, so that there are quite a few questions, some of them shown here, of what questions can be asked about how the forecasts were created, what assumptions were made. And then it's helpful to understand the details of the data center types and designs, because those have a significant influence on power demand. So there are many questions that can be asked around those areas. So with that, I will open up the floor for any questions and have some discussion. I apologize that went a little bit over time. So I'm happy to follow up with any questions that come up afterwards, available over email.
Great. Thank you, David. Anna or Deborah,